Professor Mansmann, Professor Hinske, thank you for being here today. Can you tell us what the difference is between machine learning, traditional statistics, and artificial intelligence?
Let's start with traditional statistics. I think it has a very long history. It started with counting in Mesopotamia, came to some mortality tables in England, and got more and more involved with mathematics in the 18th and 19th century. Then it had a theoretical basis. One could formulate principles. One could look what is an estimate, what is variation, what is an efficient estimate, what is a good estimate. And suddenly one could combine theory and practical data work in a very powerful manner and arrived in an increasing wealth of data, and suddenly traditional statistics was not enough. It could not handle it. And then one had to have a new idea.
Yes, and artificial intelligence is driven by the human fantasy, basically, to create machines that can think of themselves, that can mimic human intelligence and human behavior. I think one of the earliest attempts was the Schachtürke, or chess turkey, which was an invention where a figure, or like a robot, would actually play chess against human beings. And this was a very popular model. And there was like a very tiny person who was an excellent chess player, and he would actually maneuver the robot so that the robot would actually play chess. So artificial intelligence refers basically to any algorithm that is trying, or any field of study that is trying to mimic human behavior, including logic reasoning, including intelligent search algorithms, basically expert systems, where you just have a set of coded rules that still would allow you to give answers to very specific questions. Machine learning is a part of artificial intelligence. Machine learning, the major part here is the learning aspect, meaning that you have algorithms that are not specifically designed for a certain task at hand. So, for example, you don't write an own algorithm with your own rule set, for example, for the detection of sepsis. But what you have is you have an algorithm that can be trained by data, an algorithm that would modify itself, that would adjust the parameters such that you could train it for detection of sepsis. But you could use the same technology, for example, for the detection of myocardial infarction or anything else. So machine learning actually gives you a set of algorithms that learn from the data to make predictions about things that would happen or that are likely to occur.
But one could also argue that machine learning is a consequence of statistics. Because in statistics, the data are accumulated, and suddenly they have been so complex that the models offered by traditional statistics could not be handled anymore. And therefore one needed so-called non-parametrical approaches, things which do not assume models, which are open to the structure behind the data and who can provide estimates like means or very complex regression models. And this was the beginning of this machine learning. It was a random forest, it was a classification tree card. And I guess there's also the connection now to artificial intelligence. The first simple neural networks came out of a generalization of regression models and simply try to be open and not dependent on theoretical structures.
And there you have the overlap. For example, logistic regression is a classical method that if you ask a machine learner, they would tell you logistic regression is a machine learning method. If you ask a statistician, they would tell you it's statistics.
And what about the term deep learning? What's the difference between deep learning and machine learning? I understand both are part of the umbrella term artificial intelligence. Is that right?
Yes, that's true. It's actually a part of machine learning itself, to be more precise. And deep learning refers to all algorithms that basically allow you to create a stack of layers for the data processing. So the most famous algorithm it's used with are neural networks, which is probably like 90 or 95%. But you could, in theory, you could do the same with Bayesian networks. People have done it. So there's deep Bayesian networks. There's deep random forests. So you could, whenever you add multiple layers that the whole data training process goes through, then you could call this a deep framework.
And finally, what about reinforcement learning? Where would you classify that, so to say?
Well, reinforcement learning is derived from the idea. So it's also machine learning. You can have deep reinforcement learning. The idea with reinforcement learning, just like Q learning, is basically that, first of all, you think of an agent rather than just your model. You have an agent, you have a state, you have a policy. So these are important terms. And the idea is, just like you as a human, when you learn that, for example, if you put your hand in the fire, you learn, okay, that's painful. So the next time you may not want to do this anymore, right? Because your environment, you feel like, okay, this is painful, so this is not the state I want to be in, right? So your policy will include now some sort of rule that says, don't hit the fire. Mimicking the basic idea of how humans learn, you create basically an agent that can perform or suggest actions based on what the change of the state of the world around the agent was.
Mm-hmm. So a specific type of machine learning.
It's a very specific type of machine learning, mm-hmm. Yes.
Great. Are there actually instances where machine learning, artificial intelligence, deep learning should not be used, but you should use traditional statistics?
I think a data scientist would tell you there are no situations. And in a way, because data science are just taking over a lot of the thinking from statistics into this machine learning world. So actually the principles of statistics are mostly mapped into new algorithms and new approaches. But of course, there's a very famous paper by Leo Preiman. It was beginning of 2000, two cultures. One is called the algorithmic culture, which is simply trying to produce predictions, and the modeling cultures, which comes from the statistical tradition, where you try to define a model describing what you are looking at to understand perhaps mechanisms behind it. There was this difference, but actually we have to say that this kind of mechanistic thinking, where statistical models sometimes try to contribute, is now also possible in machine learning, where you do this explainable AI or explainable ML. Do I understand this very complex findings behind what a deep learning network is producing or a complex algorithm is giving you?
Traditional statistics has advantages because we are very familiar with it. We've been using it for, as Ulrich said, hundreds of years now. So people are pretty familiar with what are the consequences and what is the best way to use it and derive the conclusions that you want to. It also allows you, much faster implementation. So for example, if I want to, for example, predict sepsis, if a patient is going to be sepsis in the intensive care unit, if I use logistic regression to develop a score that gives me as a clinician some information about this, then one, I could use the score basically immediately. Second, I may have an understanding based on the logistic regression function of how much each of the variables that go into the score, how important they are. 3, I can use it on the street, basically with no computers and nothing attached. If I'm using let's say, a well-trained neural network that includes 2,000 or 100,000 variables, parameters, from the arterial waveform, etc., then first of all, even if I make that explainable, if I'm having 200,000 variables, it will still be very hard for my brain to understand how exactly did this algorithm come to the conclusion. That is one thing. Implementation will be very difficult because depending on what the data was trained on, I need to estimate the risk that the algorithm is wrong, etc., and we are only at the verge of understanding how we can develop tools that allow us the assessment for this. So the implementation, we have very different legal issues continuously, popping up You know, even the issue is who will be responsible if your AI algorithm tells you something and you do it and the patient is harmed by this action. Who's responsible? Is it the doctor who did it? Is it the company that developed this algorithm? Is it the algorithm itself? You know, if it's intelligent enough, can we at some point attribute personality and liability to the algorithm itself and punish the algorithm for doing something? So there's a lot of unanswered questions that make the implementation of such an algorithm very difficult. In the intensive care unit, for example, I'd say there's basically one system on the market these days that proves that artificial intelligence is beneficial for one very specific type of situation. So there's not a whole lot around, but we use the statistics basically every day. So I think there's, in medicine especially, there are quite some situations where, at least at the moment, we can still say that traditional statistics play a major role, and probably will for quite a while.
Mm-hmm. And maybe not just liability, but also moral responsibility.
Ethics, yes, of course.
But let's talk about the flip side. When is machine learning actually something that could be extremely useful?
Yeah, for example, to discover spam mails. Each mail program has some machine learning algorithm in it to discover spams and put it aside. I mean, you're just automatic translation of some texts. This is machine learning. Even if you drive a car, you need an algorithm who can differentiate between you have a crash or you just run over a sideboard. So you need also classification algorithms about the situation your car is in.
And you can also think of all the generative AI, you know, something that statistics wasn't developed for. For example, you tell the AI, the algorithm, you want the picture of a 30-year-old female, for example, it would generate it for you. You could use it to create synthetic patients, for example. And these type of things, you know, like what we call creativity or generativity, that's something that AI can do that classical statistics is not directly designed for doing.
I don't believe this, because this is actually classical statistics, because what you do, you have a collection of possibilities, and then you define a subspace. And in the subspace, you look for distribution. And based on this distribution, you select a possibility and you give it out. And this is actually what is happening there. But in a way, what is not traditional is a high dimensionality, complexity of this distribution and subspaces. So you need machines and algorithms doing this subspacing, the subsampling, but it's a quite general, traditional concept.
But that's true for all machine learning.
Yeah,
that's not only for the generative part.
But this is what I mean about how statistics developed ideas and concepts reached an end, and now we transform these principal ideas in a new world.
In a new space dimension.
Yeah, and have real successful translations there.
So would it be too simplistic to say, if I want a really high, a really accurate prediction model, I'm better off with machine learning, especially if I have lots of data, as opposed to I have very little data. I have to use traditional statistics without these extensions. And also if I want to explain the covariates, the association between the covariates and the outcome.
I mean, there's a systematic review about comparing traditional modeling approaches to machine learning based approaches. And in most cases, there is not a real advantage over the traditional approach, the traditional modeling. But I guess if we just conquer complexity, the traditional statistics will fail. And so we need the things. And we need the guidance from statistical principles to go not wrong in this high complexity, which is so foreign for our mind and for the way how human thinks and comprehend. Right. But I think we have, from traditional statistics, we have a lot of guidance how we can behave successfully in this very high-dimensional, very unintuitive spaces.
Especially when you think about, for example, tools like, to assess calibration, something that machine learning is not per se designed for, but very important, right? You can make potentially better predictions for your very specific subset, but if it's not well calibrated, it doesn't work in any other setting that has a slightly different distribution of your population. This is exactly the point. You can train machine learning also on small data sets, right? A neural network, you can iteratively train it. The risk that you always have is because you will have very many degrees of freedom of how you connect the neurons, for example, or how you put the weights. You have very many parameters, so you will always be in a situation where you can make extremely good predictions on this very small data set, and then end up with a highly overfitted model. Just as Ulrich said, if you have a super complex problem, if you need, for example, motive detection in arterial waveforms, for example, that's a classic use case that's great for machine learning. Image detection, if you're looking for, or image segmentation, classification, if you want to find like minor tumor residues or something in an image, that's also a great use case for machine learning. But if you're looking, for example, if you go for the approach, I want to predict sepsis and I have 20 variables and maybe I have 200 or 300 patients, then there's usually no big point in using machine learning. It won't perform better. It just gives you issues like, how do you handle calibration and these kind of things that logistic regression basically is by design gives you calibration.
Okay, I think you convinced me, and since I'm simply stand-in for the audience here, I think the next logical question would be, how do I then go about it? Should I learn traditional statistics? Should I learn machine learning? Should I learn both? Should I enroll into a degree program? Should I do a massive open online course, a MOOC? What do you guys think?
It depends on your goal. If you would like to go and take this as your professional field, you should try to get some education in data science. You should look for a bachelor or master program in this direction, because data science is now the unification of informatics. You need computers in this field. You need data processing on a complex high level. You need the modern instruments of data management and data storage. You need statistics as a source of principles. And you need these new concepts of machine learning, which gives you an incredible power on data.
And I also think that the online classes that are offered are also a great tool to get started as early as possible if you're really interested in this, because they're cheap or even free. You have lots of data available on the internet right now, even medical data that you could use. And just like any other tool that we use, we need to learn how to use it. Everybody by himself need to learn how to use it, what the upsides are, what the downsides are. I think especially with this technology, it's very important to get a hands-on expertise training.
Do you see any long-term dangers from AI?
I mean, we have had one very important case where these computers are driving the financial market crazy, where these chains of algorithms and decision tools really can kill the financial market.
Well, that's very important, because the interactions in itself, we have no understanding, or it will be incredibly hard to predict how these different systems that are continuously upgrading their level of automation or management through AI algorithms will actually interact, Just like our neurons in our brain probably their interaction creates what we think is our consciousness. Now, when we have all these AI algorithms, they also interact, just as Ulrich pointed out, but this may also affect the medical field, etc., etc. It also allows, if you go for re-identification attacks, we just had this article that allows you from MRI scans to basically remodel faces and de-identify data, re-identify data that was considered de-identified. So we might actually, in the wrong hands, these tools may be able to, from a little picture of whatever your jacket, to be like the Sherlock Holmes that would infer everything about your life, where you come from, how much money you make, if you're married or not. And that means that people may actually be exposed to threats in terms of that people could blackmail them or get information that shouldn't be there.
Professor Mansmann, Professor Hinske, thank you very much.